Okay, great. Welcome back to the final part of our lecture here. We're talking about all these geoengineering solutions. Remember, we kind of were able to sort them out into two piles. One was the solar radiation management type of solutions, and the other ones are what we're going to do now, the carbon cycle engineering solutions. And carbon cycle engineering is attempting to modify the carbon cycle so that carbon dioxide is removed more rapidly from the atmosphere. Remember, it's actually pretty slow for the natural carbon cycle to remove carbon dioxide from the atmosphere, on the order of many centuries to thousands of years to remove the kind of carbon dioxide concentrations that we're creating. That's why we refer to carbon dioxide as producing irreversible climate change. It's not that it can't ever reverse, it's just that it's going to take way longer than we can plan. So we can do things to enhance the ability of the natural world, the carbon cycle, to remove that carbon faster. For example, reforestation. When you plant trees, those trees will be extracting carbon dioxide from the atmosphere and putting it into long-term storage, and they're sequestering the carbon in the form of wood. Planting long-term forests, not something you're going to cut down in a few years for firewood or something, but something that is long-term, it will become old-growth forest someday, is a good idea. There are stranger ideas, though. For example, another thing that can be done, and is actually done on industrial scales, involves fertilizing the ocean. Now, the particular slide I happen to have here is what they mentioned in the book, which is iron fertilization, where a ship looks for areas of the ocean where the limiting nutrient in the ocean is iron, where the phytoplankton and so on would be more active if there were more iron in the water, and then they offload iron into the water. And that causes the phytoplankton, that's the nutrient they've been waiting for, and they get more active, they draw carbon dioxide out of the surface waters and so on to make food for themselves. Then either the dead plankton themselves sink and take the carbon with them down to the deep ocean, or something eats them and then poops, and the poop goes to the bottom of the ocean. But either or, that creature itself dies and sinks to the bottom of the ocean, but it results in a net transport of the carbon downward in the ocean. This particular slide said that it could be there for 100 years or more. It certainly would be more. It'd be more on the order of thousands of years that the carbon is down there. You could refer back to the carbon cycle module of the course if you wanted to see more about how that would work. But this kind of idea is called a biological carbon pump. There are, in fact, firms that do this. They go out and earn carbon offset credits, so you're going to learn about those in the next module, by going around and figuring out, hey, if there was the food web in this region of the ocean is limited by the fact that there's a lack of phosphorus in the ocean, or there's a lack of iron, or whatever, and then they provide that nutrient, and they get a bloom of phytoplankton, and the food cycle goes nuts for a while, and then eventually all that carbon ends up on the floor of the ocean. It's pretty clever. You could even throw more technology at our problem of carbon cycle engineering. For example, there's air capture. Now, all of the air capture strategies are actually pretty high-tech and experimental. None of this is done like on industrial scales yet or anything, but basically air capture is attempting to remove the carbon dioxide that's already in the atmosphere. Mostly it's done using some kind of chemical technique, where some kind of fan-looking thing here is put up into the air, wind blows through it, and as the atmosphere flows over these louvers, they're treated with something that absorbs carbon dioxide as it flows over these louvers. And there's a lot of different kinds of plans of these. Some of these strategies, when I did some looking into them online, that was a computer rendering of that air capture plant. That isn't actually done yet. It isn't as simple as you can somehow filter the carbon out of the atmosphere, but there are materials that can absorb it, and then you can extract the carbon from that material. Currently, this is not really done. All of the examples of this are demonstration technology. It takes a prohibitively large amount of energy to build these facilities, power these facilities, scrub the carbon dioxide off of these filters and filter out of these chemicals that did the filtering and so on. And we still don't really have any industrial scale solution as where we're going to hide the carbon when we're done with it, like, inject it into depleted gas fields and so on, these kind of carbon sequestration schemes that we've talked about. But in general, carbon cycle engineering looks like a pretty attractive option as such things go, since it is actually dealing with the carbon dioxide itself, not just the warming. I mean, getting the carbon dioxide out of the atmosphere also has effects for things like ocean acidification and so on that are, that's a benefit too. We like this. And actually, the public loves these geoengineering options. It's very attractive to the public because it doesn't require us doing anything. We get to still use fossil fuels, we get to still burn coal, keep coal jobs, not pay to rebuild power plants, etc. I mean, yes, we got to pay for these options, be they solar radiation management or whatever, but in general, these geoengineering things are kind of what the public is assuming is going to happen. We're going to find a way to use technology to get us out of our trouble. They also have an advantage from a political point of view, in that geoengineering options work pretty fast. If we went out and started on an industrial scale putting sulfate aerosols into the stratosphere, almost immediately temperatures would start to fall globally. If we started adding sea salt to marine stratocumulus clouds, if we built a solar shade, almost immediately we would see the difference. That's very different than those mitigation strategies where, even if we switched completely to renewable energy, it would take decades before the climate would look any different than if we hadn't done anything. Don't get me wrong, those mitigation strategies are important. They are what we need to do in the long run. But I can understand why voters don't want to pay for that, or consumers don't want to pay for that, because it's not going to show any difference in their lifetimes. It's short-sighted, but that's human nature. There's also another non-trivial benefit to geoengineering in that actually everybody would benefit from it. It's not just something that only rich countries would benefit from. It's not just something that poor countries. It actually involves making changes that help everybody. And remember, that was not necessarily the case with like the adaptation strategies and so on. So this is not so great. I mean, this is a relatively good thing about geoengineering, but let's not kid ourselves. There's plenty of disadvantages and problems with geoengineering. Probably the biggest one is who gets to decide what we end up aiming for here. I mean, the truth of the matter is, if we came up with a geoengineering scheme that would be built into this that we're aiming for some different global temperature, like the global mean temperature in 1950, or the global mean pre-industrial temperature. But you know what? No matter what we aim for, it's not perfect for everybody. There will be winners and losers with any geoengineering scheme, where somebody can say, I wish if the planet's average temperature was a ½ degree warmer than this, we'd have a stronger monsoon in our part of the world and we wouldn't have 1 billion climate refugees. Or if you only could make the water temperature, the average temperature of the planet a ½ degree colder, sea levels would be falling in my part of the world, or something like that. No matter what we pick, there's winners and losers. There's winners and losers with what we're doing now, and we're not really picking, but we would have to pick if we were doing geoengineering. What are we going to do if geoengineering ends up harming one group to the benefit of others? Yes. Cooling the planet reduced the rate at which this climate change was happening, but maybe the Indian monsoon is now failing. It's nowhere near it. They only get half as much rain during the monsoon season as they used to. We have climate refugees, we have food shortages. Who's going to pay for that? What are the ethics of all of that? You can understand that is not a simple problem. For that matter, there's all kinds of other risks to the environment. I mean, spraying sulfur into the Earth's atmosphere on industrial scales, putting gigatons of sulfur up there, has all kinds of consequences for things like acid rain, for example. All of those techniques about like biological carbon pumps that worked in the ocean when we put the iron in there, they all have environmental risks, and they are all picking which species thrive and which ones don't, and so on. None of that's easy. None of that's simple. None of that's all that ethical. That being said, most people would say that we can't really do this at this time. We got to focus on adaptation and mitigation strategies instead, even though we hate those strategies. Because honestly, we're not going to like these either when time comes. That being said, I like what your book said about the fact that in the end, this could turn out to be our last hope. If it gets to be 2050, 2060, and we're starting to see climate change and we're seeing climate change now, but we're starting to have increased climate conflict over water rights and climate refugees and extremism and so on, this could be our last hope. We might, say in the second half of the 21st century, start saying, fine, let's build a solar shade, Mr. Burns. Let's do what it takes to fix the problem now and deal with consequences. We got the whole 22nd century to deal with consequences. Oh, great, I'm looking forward to that future. Hell, I'll be dead. But you won't be. Let's do a couple questions here at the end. Question 7. Reforestation is an example of A, solar radiation management, B, a biological carbon pump, C, carbon cycle engineering, or D, a way to change the solar constant without making changes to the rate at which we burn fossil fuels. Which of these is the right answers to what reforestation is? Make a choice from those 4 options and get a little feedback before you move on to question 8.